In our last video, we explored this function and found it had a domain that was this set, right? All the points in the plane except for on this circle, right? And that was a circle centered at -1/2, 0 with a radius of 1/2. In that video, we even point out that the origin is definitely not in this domain and certainly would give us 0 on the bottom, but all the points on that circle give us 0 on the bottom of that fraction and are out of our domain. And we discovered that the range was from -infinity to 2 and from 2 to infinity, that 2 not in the range. And we saw this map of level curves where we have one level curve that is a line coming down the y-axis, and then everything else was a grouping of circles. We even talked about what z-values mapped which way. Z-values were negative, were mapped there, some positive, and then the larger positive things there, if I'm remembering it correctly, but we can kind of triage all that later. In this video, we're actually asked to take a limit or show that that limit doesn't exist. And to me, this is actually where the story started, because that was the homework question the student walked into my office with. And it was actually an online homework question, so it had parts and walked people through a calculation. I kind of want to imagine someone just asked me this question and I don't know anything about the homework problem, and I've familiarized myself with domain and range in this set of level curves and kind of want to just kind of parse it through that. And I'm thinking that there's certainly a path here where I know what that limit's going to be. As I travel down the y-axis here, all of the z-values were 0, right? This is a level curve at z equals 0, so as we approach the origin on that path, the limit is assuredly 0. But let's make sure that works out computationally. So it's I'm going to pick a path to start with, and I'm going to let that path be the path x equals 0. And so let's think about our function. All the x's are zeros. All right, well, that's 2 times 0 over 0 plus 0 plus y squared. Well, 2 times 0 is 0, and our function is just always 0 along that path. And so the limit now as as y goes to 0 of our simplified function 0 is, of course, 0. So I have a path where this limit's going to 0. So based on what I'm thinking right now is if I just find a single path where this limit does something else, we're done. And so I'm going to kind of pick the most naive next path to take, and I'm going to say let y equal x. If I replace all of the x's, all the y's with x's, this is 2x over x squared plus x plus, well, x squared. 2x over 2x squared plus x. We can definitely divide everything by an x. Now let's take a limit as x goes to 0. And we get out a 2. So along the y-axis, our limit is 0, but on the line y equals x through the domain, however I get closer to it, apparently I'm going closer and closer to 2. So by the 2-path test, this limit fails to exist. And I guess that's a spot where this video could end, but I kind of want to tell the rest of the story. Because if you just saw this, it's well, clearly this limit didn't exist. But the way this problem was stated in the homework that I've referenced was actually to first convert this to polar. And then we can take the limit as xy approaches the origin by letting r go to 0. So let's rewrite this function in polar and take that limit as r tends towards 0. All right, remembering that in polar coordinates, x is equal to r cosine theta and y is equal to r sine theta. Just plugging those in where they go, and on the bottom of this fraction, I see r squared cosine squared plus r squared sine squared, and through a Pythagorean identity, I know that's just the same thing as r squared. So here I have r squared plus cosine theta. R cosine theta. Now I observe that everything has an r in it. Could probably observe this first, but I'm going to cancel out an r. So I have 2 cosine thetas on top, r plus cosine theta on the bottom. And that cancellation was what was really important, because now I can take this limit and I get 2 cosine theta over cosine theta. And very naturally here we write, well, that's equal to 2, and it's like we want to walk away, but that makes it look like this limit exists and is equal to 2. And like, that makes me sad, because that's not what we got a minute ago. I know this limit does not exist. And so what we have to be careful about here is something that we're kind of maybe taking for granted. When we cancel this cosine theta with this cosine theta, they cancel everywhere except for where the bottom of that equation is equal to 0. 2 cosine theta over cosine theta is equal to 2 for all values of theta where this expression exists. This expression does not always exist. Notably, it doesn't exist where the bottom's equal to 0, which are at all those odd pi halves. I'm going to be very lazy here for just a moment and write theta equals pi halves, but we know that list continues infinitely. 3 pi halves minus pi halves, all the odd pi halves. Well, in polar coordinates, theta equals pi halves is an equation of a line at, well, pi halves. And now it's like, okay, well, this limit's always 2 for every path I could conceive of, except for maybe at pi halves where that expression doesn't exist, so I need to investigate what happens there. Oh, that line's the y-axis. That is the path where x is equal to 0. And we already know that limit was 0. So even though in polar coordinates, it looks like every path other than this theta equals those odd pi halves is going to 2, now I know there was a second path where the limit was equal to 0. And so again, even if we approach this through polar coordinates, by the 2-path test, this limit fails to exist.